a lot of people hope we never get a negative number under the radical, but if you do, it's not a big deal. It actually is interesting. Okay, welcome back. Last week of the year. This will probably be the hardest lecture we do today in terms of math, and I hope it will convince you that there was a reason for you all to do this stuff when you were bachelors. Now that you're masters, it's kind of assumed that you can deal with a matrix and understand what an eigenvalue is. And the reason why this is so important is at the master's level to understand what macro is about. It's about understanding the dynamics of the system. If I hit the system with a shock, what happens next? Okay, so it's not just about comparative statics now. We're talking about literally comparative dynamics. And in the past 30 years, macroeconomists use a number of new tools. One is called the impulse response function. It's a way of studying the model's response to a shock. And not just in one period, but in many periods. In fact, if you want t equals infinity, but who cares about that? In the long run, we're all dead. So the idea is to understand whether the system is stable, whether it explodes or not. If I hit it with a shock, do we have a Marxist collapse of the capitalist system? Or does the system kind of come back in some sort of wave-like function? Or does it come back in a damped way, but relatively quickly with perhaps just one crossing of the mean? Or maybe it won't cross the mean at all. So these are interesting things that we study in macroeconomics, and it's part of the introduction to business cycle theory. So any other courses you do in macro will involve putting models together and looking at their dynamic properties. Okay, so what I'm going to try to deal with today is just to introduce you in a very sort of cookbookish type of way. Sorry about that. So welcome. Merry Christmas. I can say that in Germany with impunity. In any case, I'm going to spend a lot of time repeating myself, and there's a reason for that. I want you to understand what I'm doing. And what I'm doing is basically taking this model, this sort of undergraduate model we had last time, and I'm going to force it into a form that allows us to study its dynamic properties. Okay, it's not the model, and that's important for you to remember. This is a toy model to get you thinking about it, and maybe for many of you it might be the last toy model you ever see, but many of you are coming from undergraduate programs where this is done. Some very important textbooks use this kind of thing to convey to undergraduates how to understand why inflation and output sometimes move together around trend, and sometimes they move in opposite directions. And we learned last time this is a very simple way of sorting out your thoughts. But I'm going to push it a little bit harder. I'm going to say, you tell me the model, I can derive the dynamic properties of it, and then we can study those dynamic properties, and we can even ask whether it looks like something the data would predict. Okay, so buckle your seatbelts. It's not really that hard. I just want you to be entertained this last week before Christmas, and also feel like you're getting a reward for coming. You can always watch the movie, but I'm better than the movie, I think. Okay, I've watched those movies, and even though Philip, our film director, is quite good, it's nothing's better than live, right? Don't you agree? Good. Okay. So we're going to review last time quickly. And I'm going to try to impose this belief on you that stochastic difference equations is the way macroeconomics goes. So no matter whether you believe in a new Keynesian view of the world, or you're more of a neoclassical guy, or maybe you believe in both, or maybe you believe that banks have a lot to do with the business cycle, any type of model that is modern and gets published in journals today has to deal with a stochastic difference equation. And the idea is Slutsky. Remember Slutsky said, random numbers, take linear combinations of them moving forward and backwards, and you get something like a cycle. It's an irregular cycle. This is a deep insight. And if you like time series analysis, you will have seen that already. Okay? If you're doing time series, advanced time series, it's an incredibly interesting insight. Okay? So again, depending on what we assume, we can actually generate cycles that are irregular and in principle unpredictable, not knowing the shock, but conditional on the shock, we can understand how the system moves through time. Okay? So I'm going to try to convey that notion, and I'm going to introduce you to the impulse response function in a very simple way. It's going to be an autoregressive process of order 2. So it's basically something depends on 1 period lagged and 2 periods lagged. And that's it. And if you don't shock it, it's completely stable. You shock it, it's going to take some dynamic form. And even if you just shock it one time and take the shock away, you're going to get dynamics. Okay? Now, in the real world, every day we have a shock. I told you that last time. So this is a very simple, rarefied way of thinking about macro. And that's the way policy people ask questions. What happens if we raise the interest rate in the European Monetary Union? What's going to happen to output in the next, say, 5 to 10 quarters? And there are a lot of people working on models that can actually predict that. Now, of course, that's only one shock. In the real world, oil prices might drop, they might go up, there might be a war, all sorts of things could happen with aggregate demand. Consumers might get really pessimistic or optimistic, or maybe there's a diesel problem with Germany and no one wants to buy Volkswagen cars anymore. So that's the kind of thing that we want to understand, and we don't have to assign it to a certain event. We just have a class of events, demand shocks, supply shocks, and then go forward from that. So I'm going to teach you again, just like with Ramsey, a cookbook approach. And if you like this stuff, then you can go on and do more. But you need to learn the cookbook, just like you learned how to do the Hamiltonian. Okay, so again, this has to be a master's course for everybody. Master für alle. But if you really want to go further, you're going to have to do some extra homework on your own. But this is already kind of interesting in itself. So I'm going to give you this cookbook, and then I'm going to show you that there are numbers associated with that process that actually have a certain deep meaning and has to do with the stability properties of this equation. We're going to study a single equation, and I'm going to show you at the end we can generalize that to a whole system of equations, and you get the same interesting insight. Okay, so when you go on to take Professor Weinke's course in monetary economics, you'll have a multivariate system, and you can write it in matrix form. So we will learn why matrix algebra is important. Okay, so I'm really going to stick it down your gullet today. It's important stuff, and once you get it, it's like epiphany. Once you see the characteristic roots of a system and mapping that into the eigenvalues of a matrix that summarizes your dynamical system, it's really kind of cool. Okay, so that's kind of where I want to take you today. So last week. And again, I'm very happy you came. It's very unusual for people to come right before Christmas because Christmas parties, that sort of thing. So thank you for coming. It's really touching. We talked about the Phillips curve as just an example of how you can use inductive reasoning in macroeconomics. Phillips looked at this relationship and said, hey, there's something here. But he also said we probably shouldn't take advantage of it. We should be careful. And he kind of anticipated the Lucas critique that you already know about. And we started with this ASAD model as just a way of demonstrating how you can get a shocked difference equation, but also how it can help you sort out understanding why inflation sometimes goes up and output goes up at the same time. You can think of the ASAD model as a way of understanding that, a way of filtering the data, putting glasses on and seeing what the data look like with those glasses. Okay? And then I tried to push it a bit harder and said if you want to put math into the soup, you actually get a system of difference equations. And the way I've cooked this soup is actually just so you can digest it. You don't have to do what we did last week. You don't have to solve it literally, okay? But in some sense, we're going to have to do something like that if we want to get more insights into the dynamics. So taking that simple model, just a few steps, getting rid of inflationary expectations. We had this second order difference equation in output gap. Okay, so that was kind of a neat step. And then I tried to motivate that in the writings of Eugene Slutsky, poor Russian guy who was extremely smart and actually saw this coming. He actually wanted to describe all sorts of phenomena, like, why do we have wave-like features in the data? Okay, you could even use this to think about the weather. But he was looking at a linear system, and we're going to stick to the linear world. So keep that in mind, too. The world is not linear. So in the end, we're going to be looking at approximations of the system, even if it's non-linear. So we're going to take linear approximations. We'll do that next year in January. Okay, but I just want you to understand right now, if you start with a linear system, with the shocks linear in the endogenous variables, you can actually get something like we did last week. Okay, it was a very special case. You get the AR2, the autoregressive formulation of order 2. But it has special meaning for us in macroeconomics, and I'm going to show you with real live data how you can actually get a pretty good idea of what's going on in Germany just by looking at a second order difference equation. Okay? So I've said most of this already, but I want to remind you, we're going to have deterministic difference equations to think about to fix ideas, because every period a new shock may arise. So what the thought experiment we're going to be looking at for the rest of the hour is what would happen if my difference equation, okay, so think of yt equals alpha 1 times yt minus 1 plus alpha 2 times yt minus 2 plus a shock. And I'm going to shock it one time, and I'm going to hold that shock in place, and I'm going to ask, how does the system react? Okay? That's what we call in math a difference equation, and it's an inhomogeneous difference equation. Okay, why is it inhomogeneous? If I scale that thing up, you're going to have different behavior. If it's homogeneous, I can multiply yt and yt minus 1 and yt minus 2 by some constant, and nothing changes. It cancels out. That's called a homogeneous difference equation. Inhomogeneous means you've got this constant in there which is causing you a headache. But it's actually the interesting thing for us. That's the shock that sets the system in motion. Okay? So we're going to start by thinking about an inhomogeneous difference equation. And we're going to think about that as the system's reaction to the shock. Okay? So we're going to do what's called solve. We're going to solve that equation, because right as I've described it, I'm going to come to it in a second, it's currently expressing yt, current output gap, as a function of lagged output gap and twice lagged output gap. And possibly if it's a fifth order or seventh order, you'd have even more lags. Okay? But for us, the interesting thing is first the shock, and secondly the dynamics. And we want to separate those. So that's the objective today. Okay, so we took this undergraduate ASAD model and started massaging it. Okay, we just basically solved it as what we call a univariate, because it's in one variable, difference equation, because it's not a differential equation. Differential equation would be what would happen if you let the changes in time go to zero. That would be a differential equation. Those kind of equations are really hard to solve. Okay, and the nice thing about a difference equation is it kind of corresponds to the way we look at the data. We get GDP data in Germany only every quarter. We get inflation data every month. We don't get it every instant. We don't have a continuous measure like the thermometer on your wall in your apartment. Okay, so we're expressing output as a gap, as before, deviation from the solo growth path. Now think about this. This is important, okay? We've studied the growth path for a long time. Now we're looking at the deviations, because we know there's something else in the data. We see the data looking very jagged in its behavior. So we're going to think about this output gap depending on its lag values. And the shock is a linear combination of demand and supply shocks in the model I showed you last week. Okay, so think of this epsilon as something we really don't understand yet. Okay, it's kind of a mixture of demand and supply. Go back and look at your notes from last week. Okay, so unless you have more information, for example, whether inflation is going up at the same time, it's going to be hard for you to sort that out. And the world has lots of shocks, believe me. Okay, but we're just going to consider the behavior of the system right now, just to convey the idea, just like last time, of what this difference equation does. You can do the same operation for inflation. Okay, so you can actually write inflation in this model as a function of its own lags. Okay, and you can see that there's no reason to believe that inflation and output are positively correlated. And that's what we learned before when we looked at the ASAD graph. Okay, so supply shock would imply a negative correlation between output gap and inflation, and a demand shock would imply a positive. Okay, so a positive demand shock in Germany would cause inflation to rise and in output to rise, and a recession, we would think of a demand-driven recession as being a decline in output and inflation at the same time. Okay, so that's already very useful for people who want to go into business or work for the government, be a politician, or just read the newspaper intelligently. It's already quite a bit of progress. And I do this on purpose. I don't want you to go away from this course thinking, what have I learned for life? You have learned something for life, okay? But we can do better than that. Okay, we can do better than that. I just want to show you the econometrics you learned already in this wonderful university teaches you how to do this kind of thing. So you want to regress, and here I'm taking differences of output from its trend and regressing on 1 lag and 2 lags. Okay, so it's taking an estimate of the trend and taking the log deviation of that, and then doing an OLS, ordinary least squares regression. Okay, what do you see? You see very interesting patterns across these countries. Countries that probably are very different. Germany and the United States are different. That's not just because of the language, but and France and Germany are different. But you also see that there's a pattern in the coefficients. The first coefficient is close to 1. Sometimes it's greater than 1. And the second one is negative, okay? And most of them are statistically significant. That's the stars. Okay, so that's kind of trying to drive home that this is a useful thing to think about. And I told you that last time, I just asserted it, and then I decided to provide some evidence. In many textbooks, the US GDP behavior is characterized as a second order difference equation. Now you can make it a third order because maybe the third lag is significant in the data you're using. If you have seasonally unadjusted data, you could have the fourth quarter, because you'd have every 4 quarters the season repeats itself. But those are details I don't want to talk about. So, doing something like this is something you could do in a master's thesis, but it's probably not enough to get a good grade. You have to think about it. Okay, an undergraduate thesis maybe. Okay, so how do we get there? We use this toy version of the ASAD model, and this is kind of cooked to get the result I want to show you, but many other models can yield reduced forms that are AR2, autoregressive of order 2 difference equations, okay? So this one is actually, up to the shocks, it's homogeneous. If I multiply all the variables by 20, nothing changes, okay? Lags, current variables, etc. So we think of that as a homogeneous system, but as soon as I put the shocks in, we're away from being a homogeneous system. Again, this is all repetition. And I solve it. Now, many of you may have, I hope you downloaded the most recent version of these slides, because I slipped a change in. Instead of lambda, we have theta, because lambda is going to show up here in a different context, and I don't want to confuse you. Okay, lambda is a special Greek variable we're going to assign to the characteristic roots of the system. So think of theta as my supply side parameter. Okay, it's the if you like, the rationality of expectations, or the accuracy of the expectations. So, I showed you last time that we could take this, first difference it, take the Taylor rule and put it in, you get something like the bottom line, okay? Output deviations from trend are a function of lagged output deviation and twice lagged, and a shock, which depends on a lot of stuff, okay? And I showed you that if I just take that and put in some plausible numbers for those parameters, and I shock it with white noise, you actually get something that looks like a business cycle. Okay, so this is kind of what macroeconomists like to do. And if again, I'm repeating myself because it's important. I'm going to repeat myself one more time at the end, so please write that down. So look at German data. What do you see there? You see basically something that looks like a second order difference equation. I kind of proved it to you by showing you the regression. Okay, maybe you could say, well, if I take this sample and I put in a third lag, it also is significant. Okay, just believe me, this is a nice way of summarizing the traits of the data. Okay, so if you think about that shock, it's a mess. It's a function of the demand shock in its difference and the supply shock. We're not going to spend any more time talking about that now. Just think of epsilon as being the thing that's pushing me away from the steady state. Because the steady state is the same thing. Hi, good to see you. Merry Christmas. You're on TV. No, you're not. Okay, so the shocks, as long as they're non-zero, are going to be moving the system around. And you can see that it's the difference of the demand shock that matters. in this model. It's not the level. It's because we kind of have this neutrality built into the model. In the long run, demand shocks have no influence on output. It's the shock is the change in demand, the change in D, which kind of corresponds to what we see in the data. So like Trump has cut taxes, he's stimulated the military spending. That's had a big effect on the US economy, but now we're probably going to get a hangover. I mean, this model, if you think this model is a serious approximation of reality, would imply kind of a letdown, like a hangover, okay? Think about that, okay? Whereas ST doesn't have that property. But that's really specific to the ASAD model, and I'm not going to discuss it. I just want you to understand the stochastic difference equations. That's the important thing. So YT is a simple function of one-slagged and twice-slagged YT. The question is, what are those parameters? And then it gets interesting, okay? Why is it interesting? Because those parameters will tell me about the dynamic behavior of the system. And it's in a very efficient way I can summarize all this dynamic stuff. So now we're going to do a little bit of interesting stuff that you've never seen before unless you're a time series spezi, right? If you're doing time series, maybe you got this stuff already. We're going to make use of the lag operator. The lag operator is simply a linear operator that operates on a series and gives it the previous period's value. Okay, so it turns out that linear operators in mathematics are quite interesting, and they're called linear operators for a reason. Okay, if you apply a linear operator to the sum of two variables, you get a linear combination of the linear operator applied to those two variables. Okay, and you can also apply this linear operator many times. So if L is a linear operator, L squared is a linear operator. It's the twice lag of the variable. Okay? This sounds trivial, but believe me, you're going to see how it really helps us very, very much. Okay? Because when I get to the cookbook, we're going to think about this lag operator in a very special way. Okay, that's kind of what I just want to get you excited about this. There are other types of linear operators in math. Differentiation is a linear operator. Integration is a linear operator. The expectations operator in mathematics is also a linear operator. Okay, so if you got that, you're about home when it comes to math and economics. I mean, you can do all sorts of other fancy stuff with functional analysis, and if you want to be a theorist, yes, okay. But if you just want to think about what we're about to do with these data, this is already pretty good. Okay, lag operator L. Okay, the cool thing about the lag operator is we can do algebra on it. We can actually perform algebraic operations. So 1 minus L times 1 minus L. You can actually multiply that out, and by magic, you actually get a second order function, second order lag function of the original variable. Think about it. I can multiply yt by 1 minus A L times 1 minus B L, and then I get something really fancy. I get a quadratic form in the lag operator multiplied yt. So I'm going to give you some examples in a second, but if you just look up there, you can see it already, right? It's already there. So we can factorize these things as well. We can explode a quadratic form into a product of two. If we can factorize, okay, and we will be factorizing in a second, we can express a quadratic form as the product of 1 minus a constant times L times 1 minus another constant times L. So if you remember algebra from high school, factorization was a neat way of solving quadratic equations. It's exactly what we're going to do right now. Okay, so if you remember, oh yeah, I remember that. I remembered it from my Abitur, and then I forgot it, right? Well, I'm going to remind you. And if you went to school in other places, you probably have the same issue. Okay, you're going to have to remind yourself, and Andreas will be there to remind you. Okay. So let's give an example. Let's put an example to work to help us understand this lag operator business. Okay. So an AR process is simply Y. Again, deviation from the trend, because we're talking about Makrokonjunkturlehre. We're talking about business cycle analysis. Okay. Deviation from trend as a function of its lagged value plus a shock. That is a valid stochastic difference equation. It is a first-order stochastic difference equation. Okay? It's nice to have, but it's not adequate to describe most of the stuff that we play with, but it's a neat start. It's going to help you a lot. Okay? So I'm going to cook this thing to be stable, and I'll show you why that's important. Alpha has an absolute value that's less than 1. Alpha is a real number, not an imaginary number. Okay? And epsilon, oops, something's going already. Too bad. This is really getting exciting now. Epsilon is a random disturbance. It's a random number. And I'm going to tell you it's white noise. Because I'm pre-cooking this to get an interesting result that you can look at. It doesn't mean that's the way the world always is, but it's a good way to start. Okay? We need more information. We need to know the initial condition. We need to know what Y0 is. Because if you don't know what Y0 is, how are you going to get going? You have to know what you started with. You have to have a past. Everybody has a past. Every time series process has a past. And if you don't know that past, you're not going to be able to say very much. Okay? So we need to know what Y0 is when we start. And then we can let this thing roll. What is epsilon 1? Okay, that gives me basically a value of Y1. Because I know what Y0 is, and I know what alpha is. Okay? So that's what we call the history. Okay, so look what I do with the lag operator. I'm going to substitute L times YT for YT minus 1. Okay, that's trivial. That's what the lag operator does. I'm going to now show you that this endogenous variable actually depends on the whole history of epsilon, not just this current period's epsilon, but actually the whole history. Logically, you should understand that. Before I start manipulating this lag operator, I'm just going to show you there are many ways to show that YT, as I've written it down, actually depends on the infinite past of epsilon. Getting rid of the lagged endogenous variable completely. Now, how do you do that? Well, if you've never taken this course, anybody can say, well, just substitute. Okay, so we can do recursive substitution. I just take YT, express it as alpha times YT minus 1 plus a shock. And then that must be also true in YT minus 1. So I can write YT minus 1 as alpha times YT minus 2 plus the shock in T minus 1. And then I can take YT minus 2. I mean, this is not rocket science. You just keep doing that, and then you substitute. Okay? That's easy, right? So you get this nice expression. And you can see there's still some memory of the past in there. So in some sense, we want to eventually forget. We want to forget. The memory is there, but we want to forget that. And that's like saying, if I'm allowed to go to infinity, I can make that first term go to 0. I can literally make it go to 0. And if you think about it, the whole world is like that. I mean, this building was built in 1905. Okay? It's still around. So we're still carrying, this chapel was built in the 14th century. Right? Spätgotik. It's still around. So with different degrees of memory, the system will kind of remember these shocks that happened. So building this building was a big shock in 1905. Great for the construction sector, great for Berlin, great for the Kaufmannsverein, whatever it was, the Chamber of Commerce of Berlin back then. Similarly, the Gothic shock in 1348 was important. It was also during the plague. It was kind of hard to find labor back then. So all these things matter even today. We're still hearing the echoes of the past. So that's kind of what macro is about. We have to agree that in some sense this memory exists, and the shocks of the past still kind of ring today. Okay, that's kind of the nice intuition to get going. So you can see that alpha less than 1 in absolute value is absolutely crucial for me to do that operation. Otherwise, I have a real problem. Okay, so I'm basically trying to convey to you that stability of this AR1 imposes that alpha in absolute value is less than 1. Okay, so that's going to be very important. So you could almost say already the root of that very simple system is alpha. Okay, and alpha less than 1 is a precondition for stability. It's also a precondition for me to go into this infinite lag mode and express, because in some sense, even if we had a bad shock in 1348 with the plague, eventually it will play out. Okay, that's a key attribute. So stability also what we call covariant stationarity imposes this alpha property. Okay, now I'm going to use the lag operator to get very quickly to this result. Okay, I'm going to divide by 1 minus alpha L. Okay, it's algebraic division. It's like long division when you were in high school. When I was in high school, we did actually when I was in grade school we did this. This is how you divide 6 by 4, okay, or 50 by 23. Okay, so I'm going to show you the American way. The Germans do it slightly different, but you know, many of you actually come from third countries, and you all have your way of solving these things. But again, I just want to assert that as long as lambda is less than 1 in absolute value, I can do this. Okay, and it's, for those of you who do math, it's the Neumann expansion. It's the same thing. Okay, but I'm going to show you. Just try it. Okay, so I take 1 minus L and divide it into 1. Remember, it's a linear operator. I can do this. It's allowed. So I get 1. I put in 1, multiply by 1 minus alpha L. Subtract. What do I get? I get minus, and I get alpha times L. So the next step would be to divide 1 minus alpha L into alpha L. Okay, so you're going to get basically alpha L. And keep doing that, and you get basically what's called this long division polynomial Neumann expansion. Okay? Look carefully at that. It involves powers of the lag operator, which is basically an expression for lags of the variable, and powers of alpha. Okay, so it has exactly this geometric declining pattern that we predicted just by recursive substitution. Okay, so stare at that for a while. That is a powerful result. It is exactly the same thing as we had before. You can express this as a sum of powers of the lag operator multiplied by a constant. And that's exactly what we wrote out using recursive substitution. So this long division in the lag operator actually can be done for any polynomial you want to try. The problem is it's kind of nasty. Okay, so I'm going to show you how nasty it gets when we get to second order. Okay, so if you understood that, that's great. If you remember division in high school or in grade school, probably, I mean, I learned this when I was in 7th grade. I didn't learn the polynomial and the lag operator. I learned how to divide 7 into 4. Write it out, right? Multiply, subtract, next step, right? You've all done that before. Don't look so puzzled, man. It's going to get worse. Okay, so just want to show you that you can't do this. It's not convenient to do this even in the AR2 case. It works for the AR1. It's easy. Okay, but let me just summarize what we know. We know kind of you can take this this result we've shown, and we can plug it back into our formula, and you can basically assert correctly that YT, okay, is an infinite sum of lagged values and current values of coefficients that multiply the same coefficient that multiply the shocks of the past. Okay, so this is called the moving average representation in economics. Before we had an autoregressive, now we have a moving average representation. Moving averages can be different. You can have a finite moving average. This is an infinite moving average. Okay. Good. So this is easy. Geometrically declining weights on the shock. Again, that's why it has this sort of built-in stability. Okay, you can imagine if alpha were greater than 1, we'd have a problem. The thing would explode. One shock would be enough to make the thing blow up. One shock, and just imagine all those shocks happening, would be a total mess. So this is one way of thinking about Slutsky. It's the easiest way to think about Slutsky. It's a formalization of his vision, his assessment of the world, especially economics, shocked difference equation systems. So this is just to get you going. Now we're going to try to go a bit further now, but I keep showing you this picture. Think of the black box. Think of our model. That's the economic model. That was ASAD. We have the shocks coming in that we can't predict. Now, if I tell you a secret that there's going to be peace in North Korea and South Korea, that would have a huge effect on the world economy. But I can't tell you that. I can use a model to predict what will happen, but I can't actually tell you. So don't expect economists to predict the shocks. Our job is to figure out the black box. Now, I'm being very pedantic, but you know, I'm on film. Maybe someday someone else will watch this when I'm long gone. It's kind of an interesting point, right? I think Slutsky had it right. At least at this level of sophistication, you could say, well, maybe we can use machine learning to learn all sorts of stuff. We need the data. We need the computing power. This is all we can do right now. Let's think about that. So let's push this a bit harder. This is a useful result. We get a converging geometric series of weights on the shocks. You can generalize this. As long as the process is stable, it can be generalized, okay? But how do you do it? So I'm going to show you how this gets ugly very quickly, okay? And then I'm going to show you why we use factorization to look at this. Okay, so bear with me. I know this is kind of, maybe it's boring, I don't know. I always thought it was kind of fun. I've been doing this for 25 years at the Humboldt University. This lecture has been accompanying students for a long time. Maybe that's why I get so many doctoral students. In any case, let's look at the second order case. This is the one that we're interested in. This is the one we care about, right? This is the one we showed the data kind of support this as a way of representing the data. Shocked second order process. So we can use the lag operator as before. We factor the yt to the left-hand side, use the lag operator, so we get this polynomial in the lag operator. Okay, 1 minus alpha times L is also a polynomial in the lag operator. It's order 1. This is a polynomial of order 2. It's another way of saying second order difference equation. Okay? You can also invert this. But how do you evaluate it? So that's the trick. Okay? It's easy to show, we'll show it in a second, that Y is still a moving average of past shocks, but it's a very complicated moving average. It's not as easy as the geometric, you know, it doesn't work like that anymore. It can be very fancy. One shock can put all sorts of spin on the variable. It can make it go like this, make it go like this, make it like this. Okay, so that kind of adjustment is what turns us on in macro. That's what we get excited about, right? If Germany goes forward with you know, the Kita program and they start hiring lots of people and it's a huge shock, maybe 10 billion in people that are going to hire in the next few years, that could have a huge effect on Germany, right? Giving a lot of people money and they go out and spend it, possibly a demand shock. It also might be a supply shock. It may withdraw people from other fields and make the labor market really tight and workers start asking for higher wages. So all these things can happen. Okay, well, all I want you to think about is just think about the shock and the dynamics. So that's kind of what we're doing this. So we still have a moving average, but it's more complicated. You could try to do what I did before with polynomial division. It actually does work, but you get something that's completely uninterpretable. You'd have to really you'd have to have this sort of, you know, vision where you can actually recognize patterns, and believe me, it's not so easy, because once you do it, you get a nasty expression, okay? Look at that, okay? So you can see that it's still a moving average, because you see L squared, you see L cubed, right? So indeed, we have what we want, but not easy to interpret. Okay, so it's nasty, right? I've been using this slide for at least 10 years, and usually people laugh, but usually I don't do this before Christmas. Oh man, I'm hot today. Okay, so the second possibility, which I strongly recommend that you think about, is called factorization. So because of the algebraic notion of this lag operator, we can massage it in a special way. We can take this polynomial and factorize it. And a second order polynomial in the lag operator is easy to factorize. Third order, you might have some problems, okay? Sometimes we have to use a computer to help us go further. But I'm telling you right now, to get the intuition down, we're going to stick to the second order case. So it means basically writing the left-hand side of that equation in the right-hand side form. It means writing, okay, I give you the model, you solve for alpha 1 and alpha 2, and I'm telling you there's a unique lambda 1 and lambda 2 that makes that work. It's called factorization. Okay? And you can see that in this particular case, it's easy to express alpha 1 and alpha 2 in terms of the lambda 1 and lambda 2. Now, there are many ways to get those expressions. You might want to go home and use your memory stick. I'm talking about this one. Remember the quadratic formula and just substitute, because those are defined. Alpha 1 is defined as the sum of lambda 1 and lambda 2, and alpha 2 is the product with a minus sign in front of it, of those two so-called characteristic roots. Okay, so the solution, that solution is basically expression of this second order polynomial as a product of two first order polynomials in the lag operator. Okay, and that's the magic. Solving for the lambda 1 and lambda 2 is your ticket to understanding how this system works. Those are called the characteristic roots. And it turns out that they don't have to be real. They can be complex conjugate. They can have imaginary parts. And if they do, that sounds like a nightmare, but it doesn't mean that the economics that we're doing is imaginary. It just means that the dynamics have a special form, sine and cosine waves. Okay, so it's basically the solution to the difference equation under certain conditions may have complex conjugate roots. And if it does, if I shock it, I'm not going to get this. I'm going to get a wave motion from one shock. And if it's damped, that means we're stable. Okay, so getting your hand on lambda, getting your handle on lambda is the whole point. It looks like a little handle, doesn't it? Lambda 1 and lambda 2. If you can find out what those are, given the model, you've discovered quite a bit about this dynamical system. So to impose stability, it should be clear to you that it's going to require those lambda to have certain attributes. Okay, I'm going very slowly now because this is extremely important. And if you take any other course in macro, you're going to have discussions of whether the eigenvalues of the matrix that we're looking at are stable. Now, what does that mean? That means that these lambda 1 and lambda 2 have to lie inside the unit circle. They have to have a modulus of less than 1. It's like the alpha before, except now it could also be complex conjugate. So we have to discuss that. And that is one of the most interesting cases. I mean, if you get this kind of wavy response to a single shock, we talk about it all the time. Look at the United States had this huge housing boom, and then it collapsed, right? And we're still feeling it now. But now there's a boom in housing again in the United States. Okay, you can use that it's not exactly proof that it's true, but it's certainly consistent with a shock having reverberations that move you around the 0 point for a long time. Okay? All right, so let's look at this carefully. If you express the left-hand side in the right-hand side form, you can imagine that inversion of the left-hand side is the inversion of the right-hand side, which is the inversion of the two products, first-order polynomials in the lag operator. Okay? Inverse of the left-hand side, inverse of the right-hand side. So the analysis I did before that was so easy for you is exactly the same here. I just have to know what those lambdas are. I just have to solve for them. Okay? Because I can write that like that. It's beautiful, right? So now I've got a convolution, we call that a convolution of first order polynomials in the lag operator. And those lambdas are special. I already told you they're called the characteristic roots or the roots of the autoregressive process. And we really want those things to behave properly. We don't have a shock in our model causing an explosion. Like I said, Karl Marx thought that was the end of capitalism. We still haven't seen it yet, so I'm putting my money on Paul Samuelson. Paul Samuelson said, if the system is stable, it's got to be stable. After all these years, maybe there's something else in there that I haven't seen yet, but if you're in the middle of macro right now, this is the way you want to look at things. So we're going to impose, and we're going to look at models that impose stability of the system. So they impose that this lambda 1 and lambda 2 actually lie inside the unit circle. Now, if lambda 1 and lambda 2 are real valued, that just means that they're less than 1 in absolute value. But if they're a complex conjugate, we have to think about other stuff. And I'm going to get to that in a second. It's really important. Okay, but we still have confirmation for what I said before. Now we have a double sum. That's what a convolution does. Gives us but look at that interesting pattern of lambda 1 and lambda 2. If you think about it, it's they're kind of like a binomial type of formula. Okay, so you can imagine a lot of action could be coaxed out of that system. But it's still an infinite moving average of the past. Okay, and again, we're going to spend a lot of time thinking about this. We're going to think about the way y responds to a single shock. Okay, we're just going to hit it one time and see what happens. That's the magic of the dynamics of the system. So for that reason, we need to think about an impulse response function. That's what an impulse response function is. I shock this model once. What happens? What happens not just to one variable, to all the variables? And my model better be good, because it better tell you the right thing. So if I have a model with monetary policy, and we kind of think intuitively that interest rate increases cause economic activity to slow down, okay? And you probably could write a model down where it doesn't. It's not the case, but generally most models I know predict that. So you'd expect that to happen if I shocked monetary policy with an increase in interest rates. Okay, that's just an expectation we have. So a lot of what we do in empirical work is we try to verify the behavior of the behavior of the model is consistent somehow with behavior of the data. Okay, so you can write this out, and we have, what I've done before is just, you can think about those Greek nus as just different combinations of lambda 1 and lambda 2 in different powers. And we call that basically, we use that as a tool. It's the impulse response function. So if I tell you there's only one shock in T0, then I can basically look at the sequence of nus, and that will be the prediction of the effect on output until the end of time. Okay, that's what this thing does. This is called an impulse response function. And even if this is where it gets interesting, even if those roots are complex conjugate, the nus are not. The nus are real valued. So that's where it gets kind of interesting. So even though I show you that the lambda 1 and lambda 2 have an imaginary part, they're going to square with each other in such a way that powers of those things still give us a real solution. Don't worry, we don't live in an imaginary world. Okay, so it's going to be a really clean, and this is another way of reminding yourself what a cosine and a sine function does, because that's where it comes in. Okay, so let's go back and just remind what we had before. This is an operationalization of what I just said. Okay, so if I take the previous case, the univariate case, and I just solve, my impulse response function would look like that. Okay, so most of economics doesn't consist of AR1 type of processes. So we think the world is more complicated. So this may not help you very much, but it'll help you understand the intuition, because everything will look like that in the end. It's a key tool in macroeconomics. Okay, so you can either think about it as a response to a permanent shock or the response to a one-off shock. Usually we think about one-off shocks. Okay, so now how does this get back to where we want to go? We want to look at the dynamics, and I'm going to basically now push this to the limit. I'm going to show you what these lambdas look like and how I can plot them in a Cartesian plane. And that plot in the Cartesian plane has special characteristics, because we know that the lambda has to have a measure, a distance from the origin that's less than 1. But if you have complex conjugate parts, it's a little bit trickier, but you can still do it in the Cartesian plane. It's going to be the distance to the origin. Okay, and it has to be closer than the unit circle. The unit circle is the set of all points that have distance of 1 from the origin. Okay, so that's how we're gonna go. So let's go back to cookbook. Okay, I told you I was going to give you a cookbook. Here it comes, and I've already told you how to do it. You just have to do it. Okay. Let me just explain one more thing. There's a very important result that we're going to use, which is this. We want to solve this equation. We want to solve this yt equals alpha 1 times yt minus 1 plus alpha 2 times yt minus 2 plus epsilon 0, single shock. The solution to that, what we call a solution in economics would be expressing yt as only a function of time and the shock, not a function of lag values. Okay, so that intuition means it's like getting rid of the endogenous variable completely. And can I do that? Well, you can if you do what I just said. You have to solve this difference equation. Okay, we have to, and I'm going to take you through sort of the steps, and then we're going to see what that is. Now, to do that, I need to make use of the following. If I have two solutions to a difference equation, the sum is also a solution. Okay, and if you do physics, I think it's called the superimposition or superposition principle. Not important. But we're going to use that, however, because there are two interesting properties of that difference equation. One is that, what is the steady state? What happens if you're not having any more, when yt is equal to yt minus 1 equals yt minus 2? That's called the steady state. We know that from earlier in growth theory, okay? That's easy to do. That's one solution. If I plug in that value, it works. That's what a solution means. If I plug in that function of time and constants, it works in that expression. You can go home and try that, okay? The constant, the steady state, is a solution to this difference equation. It's what happens when all the adjustments finished. And it will take forever, okay? But it's a solution. And what's left is the deviation around the steady state, and that's also a solution. So I'm going to use the superposition principle, and I'm going to unpack this the solution by expressing it as the sum of a particular solution, that's the steady state, and the stuff that's wiggling around the steady state. And that's called the homogeneous solution. Why? If I multiply everything by a constant, I get the same thing. That's what homogeneity means. Okay, so if I multiply yt, so again, we know this difference equation has this wonderful property that if I have one solution and another, I put them together, it's also a solution, and that's the complete solution we want. It has the steady state built in, it also has the dynamics. Okay, so step one, find the steady state. Find the particular solution. That's easy. This will probably be on the exam. Okay, I'm going to give you a difference equation, and you just have to, it's easy, right? The next part is tricky, because the difference is also a solution. Okay, so we're going to think about the deviation of yt from its steady state. It's exactly like asking about the business cycle. Okay, so if you take the shock away, we're back to a zero. We're back to a homogeneous equation. So understand what I'm doing now. And then you have to look at the lambdas. So then you have to find the lambdas given what you've learned, okay? Because the homogeneous solution is the sum of powers of lambda. Think about the easy one, the AR1 case. Powers of lambda was a solution to our equation. How far you are away determines how quickly you're moving towards the steady state. You'll never get there because the limit is reached in t infinity. Okay? So in this particular case, we have two characteristic roots. We just need to solve for them. Okay? And it turns out that if you tell me what alpha 1 and alpha 2 are, I can tell you what those guys are. Okay? That's just using the quadratic formula we have in algebra in high school. Okay, so lambda 1 is a function of alpha 1 and alpha 2, and lambda 2 is a function of alpha 1 and alpha 2. And look at it, you got this square root. Okay, square roots are nasty if you have negative numbers, but they do work. We have a theory about that. It's not even a theory, it's just a way of thinking about the world in these cases. Those are called imaginary numbers. So, a lot of people hope we never get a negative number under the radical, but if you do, it's not a big deal. It actually is interesting. If you have a radical with something underneath that's negative, that means there's a plus and a minus, and they involve the same thing. Okay, so that's going to tell you why the imaginary number kind of disappears in some sense, and then we've got some interesting dynamics, potentially with damped waves. And why damped? Because if the thing explodes, it's not damped, and we want to be stable, so the thing has to converge in some sense. Okay, we have to get arbitrarily close to the steady state or to the inhomogeneous or particular solution as it's called here. Okay, so let's just do it. Let's just do that. First, the lambdas can be real. They can also be complex, conjugate. Conjugate means you've got a plus and a minus, a constant times the imaginary number, the square root of -1. Okay? And what happens if you multiply the I with itself? What's the square of I? It's -1, right? So it's kind of a convenient thing to know. Okay, so if you get powers of I, even powers will either be 1 or -1. Odd powers, not so good. But we don't have to worry about that, okay, because it comes in pairs. And basically, if I just write them down. It could be, 0.2 plus or minus 0.7 times I. Or it could be something else. I'm going to show you, all those things have two components. One is real and one is imaginary. And Descartes and Euclid, they gave us the tool to look at this. It's the plane. So you plot it. Okay, so you plot on the horizontal the real part, the coefficient on the real part, that's the number itself, the real part, and then the number you're multiplying I with. That gives you the vertical displacement from the origin. Okay? So the unit circle in that Cartesian plane is the set of all points that is closer to the origin than that circle. The circle is a set of points with distance exactly equal to 1, and everything inside of that has distance less than 1. Okay, so that distance is a Cartesian distance. So the distance between 0 and h nu, this v thing, can be expressed easily as the Cartesian distance. And that is exactly the modulus, or the equivalent of an absolute value if you have complex conjugate numbers. Okay, so that's as soon as you see a root that has a plus or minus nu times I, that means you're not on the x-axis anymore. So you can't just use a trivial test of whether the roots are greater than or equal, or greater than or less than 0. You have to look at the complementary part, and it's like using your old Euclidean friend, the distance function. Okay, so the distance of nu, h nu, and h minus nu, those are complementary. They're complex conjugate pair, is exactly the square root of h squared plus nu squared. Okay, so that's the acid test of stability, is getting closer to 0 than the unit circle. So this means that even if I have complex conjugate, and I'll show you why the complex conjugate implies a sine curve in a second. Just let that go into your head for a second. That's really important. The distance to the origin is crucial, because in the end, powers of those roots will be determining the dynamics of the system. Powers in time of the roots that we're solving for. Now, to understand that, and to understand why that modulus is so important, we want to use trigonometry. Okay, so we have to use cosine and sine. Okay, so now you understand, I don't want to have I hanging around in my solution, because I don't need to, but I have powers of complex conjugate numbers in pairs, and those products, those powers of the root will actually imply a function of time that has wave-like function, or wave motion. And the reason for that is that I can express a complex conjugate number in trigonometric form, or polar form. It's the same number. I can just use a cosine function and a sine function. Now that is really cool. Okay, think about it. The distance, the distance of, and I'll show you this. You remember the cosine sine function, the square of cosine theta plus square of sine theta is always equal to 1. Hello, that's also kind of relevant here. Okay, but just look at this very carefully. If I want, I can use the polar expression of this, h plus nu times I, but I could also just express it as in the form of cosine and sine. Okay? So how do I do that? Cosine theta plus I sine theta is the same thing as h plus nu I. Okay, they're the same expression. And there's let's go back and look at it again. Okay, so I've basically expressed lambda 1, 2 as the product of this r times cosine theta plus I sine theta. R is exactly the distance, the Euclidean distance to the origin. So R is the modulus that we're thinking about. Okay, so it's exactly the same expression, the expression of the same object. You're just using cosine and sine functions to express that. And why? I mean, if you use the Cartesian coordinate, you have a horizontal displacement, you have a vertical displacement. You give me those two displacements, and I can write that as a function of the angle theta, okay, that ray makes with the horizontal axis, and the distance. Okay, so you give me h and nu, I can give you back r and theta. Okay, so it's by definition, that's how we define cosine and sine. Cosine of theta is h divided by r, and the sine of theta is nu divided by r. Okay, so that's just a fact. So if I can take powers of lambda 1 and 2, then in some sense maybe it has to do with this cosine and sine function. And I'm going to show that to you in a second. I'm just going to show you that that's the case. The easy way to do this is to use what's called Euler's expression. Okay, so Euler, this Swiss mathematician, actually figured out that not only can you express complex conjugate numbers like that, you can also use E, his number raised to a power of t and theta and I. Okay, so that's the equivalent expression. It's called the Euler form. Okay, so it's the same distance from the origin, r, times e raised to plus or minus I times theta. Okay, so that's again, proving that is a little bit harder, but it's also easy to show. You can use the power series expansion, you can show that easily. Okay, and if that's the case, taking powers of lambda, because we need powers of lambda to think about the solution. Remember, that's the whole point. Powers of lambda is equal to powers of the right-hand side in t. Okay, so lambda to the tth power, as you move through time, is equal to r plus times cosine theta plus I sine theta, all raised to the tth power. But then again, that is equal to r to the tth power times this cosine sine function, now expressed as theta t and I sine t. So again, the first part you can see is looks like something that's periodic. The first part is r to the tth power. So if r is greater than 1, we're in trouble. The wave function will explode. If r is equal to 1, then we're going to have waves forever. If we impose some sort of stability, r has to be less than 1. And r is just the distance to the origin. Okay, so now we've gone full circle. The stability of my equation, regardless of whether I have complex or complex conjugate roots or real valued roots, it depends on r. Okay, so that's the acid test for stability in our field. So let's do this now. Let's play with this. I want to prove to you now that the lambda is what matters, and the cosine part you can rewrite this and get rid of the I sine theta. Okay? That's the most important part, because a lot of you are like staring at me, what in the world? Why am I wasting this time before Christmas? I could be shopping right now. Listen to this even if it's true, God, it's just boring as hell. Okay, but I want to make you excited about this, because powers of lambda is what makes the system run. The solution of my difference equation is going to be powers of lambda in t. I'm going to have a function that expresses yt at any point in time as a function of the shock, because of the particular solution, and this dynamics, which is a function of lambda. Powers of lambda. And we have two lambdas, I told you already. right? So we can have powers of lambda. So these lambdas, they better be tame, they better not explode as we raise powers of t, they better get smaller and smaller, but they might get smaller and smaller in some sort of clever looking wave function, or they may actually just die down very quickly. Okay, so let's look at that. The complete solution is exactly the sum of the particular solution, that's the steady state, that's the first part, epsilon 0 divided by 1 minus alpha 1 minus alpha 2. That's the, if you take away all the dynamics, that's all that's left. That's the steady state. And the superposition principle says I can add this homogeneous part, which is powers in time of these characteristic roots. Okay, and you're still, you still haven't proved anything. You haven't proved that the I goes away? Well, I'm going to do that now. I'm going to show you the I's actually disappear. Okay, but again, remember the root is a defining attribute of the solution of the difference equation. So you're going to have to find those roots, and you have to do some quadratic formula and the rest. The particular solution is the steady state, and it might be 0. Okay. But again, we think of a shock system. The shock puts us in motion, and then we have some convergence. Okay, so that's the homogeneous. That's the one we really care about. Okay, so this is the same roots we derived earlier. This is the exact same thing. Now, we already said they can be complex, or they can be real value, they can be complex conjugate. I'm going to tell you what I'm about to show you. Okay. If the lambdas are both real valued, then the impulse response is kind of boring. Okay, it might actually have a hump. It may cross the 0 line once, but it's not going to be it's not going to be a wave like you like to think of waves. On the other hand, if we have complex conjugate roots, we have oscillations. Then it gets exciting, because I mean, all of us we'd like to think that, you know, the boom and the bust cycle. You know, even if we could stop all the shocks, we'd still have some kind of cyclical. Again, we don't. To show that, you really need to know more about the data. But I want to open up this possibility to you. Okay, so how do I do that? How do I show that the sine function goes away? The I sign disappears. Okay. Well, all you have to do is rewrite it. Turns out you just have to plug it in and rearrange, and the I sine theta and minus I sine theta cancel. And all that's left is a cosine function. It's a displaced cosine function. Okay, so remember, waves look like this, and if you push it a little bit to the right, it's the same wave, but it's just moved over to the right. So we can think of taking you can take any cosine function and shift it long enough it looks like a sine function. So basically we've spanned all the possibilities. So look carefully at this, and you see that to get the stability, all we need to look at is the R. The R is actually totally decisive. If R is not less than 1, then the wave is going to explode, if we have a wave. Okay, and this is the case in the complex conjugate form. We have this, and these kappas are just coefficients, basically. So you can write, you have basically eliminated the real part just by defining my kappas in a certain way that guarantees that it's a real valued function. And it is a real valued function. I mean, the business cycle consists of real data. Okay, so you just have to go back and, okay, so I tell you what lambda is, and you go off and calculate the distance. Okay, so you use h squared plus v squared, or nu squared, and take the square root of that, and you can see whether the thing is stable, and then we're good to go. But we can do more. We can actually, and I wouldn't expect you to memorize this. Some of you already know it because you did trigonometry in high school, but it's kind of interesting to know that we can take that expression and write it in terms of a cosine function, a displaced cosine function. It's got an amplitude, okay? And you can see the amplitude is getting smaller as time goes on because r is less than 1. R is a real valued number. It's the distance to the origin of the root. And they come in pairs, okay? The angular frequency tells me something about how quickly, how frequently the process crosses the origin. Remember, I'm going to show you a picture. We have a periodic function. Periodic function means it keeps repeating itself. Okay? And if you wait long enough, it's going to repeat itself as many times as you want. Okay? But how many times it crosses the origin in a unit period of time is the frequency of the wave. Okay, and that's really important because we think of a business cycle, we think of frequency. how long does it take for the German economy to work through a complete business cycle? Well, it's not a deterministic function because the German economy keeps getting shocked. But if you only had one shock, you could make a prediction on how long the cycle would take to work through. Okay? How long does it take for having reached a peak to reach the next peak? Okay? And that has to do with the angular frequency of this, because that's the function of h and nu that we talked about in conjunction with r. Remember, cosine of theta is equal to h divided by r. That's the definition of a cosine. Okay? And the sine is the rise, the nu. Okay? So here's a classic function called a wave function, a cosine function. And I've basically set a equal to 1. And I'm going to ask Andreas to show you some other examples. 'Cause, I mean, a lot of you have done this, but it's so easy to do. So you just go plug in your computer, fire up Excel, and just use the cosine function and put time on the horizontal and just plot that thing. It's just so beautiful. Okay? So that's what I did here. So periodic function, and if r is less than 1, the thing's going to damp down. And remember, the characteristics of those waves depends on lambda 1 and lambda 2, which depend on alpha 1 and alpha 2, which depend in turn on the model we're playing with. So I've reversed engineered basically the process by which we can get a wave function response to a single shock. Okay? So let's review this quickly. It's sensible to think about the economy this way. It's the way we do it. We have models that do that, and that's what the model embodies a theory, and the theory is a way of thinking about economic causality. Okay, so that's basically where we're coming from. I'm trying to impose Slutsky's view of the world on you, and I think that's the best game in town right now. There are a lot of people have interesting ideas, but I don't think they're marketable yet. You know, some people think we can actually simulate, like Matrix, we can simulate the economy completely. Well, good luck. Computers are still not quite powerful enough to even solve some of these simple models. Even if you have complex conjugate roots to your dynamic system, it's still okay. We're not going to get imaginary values of y. Okay, it's just a way of sorting out this dynamic behavior, waves. Okay, and cycles can be irregular if you keep shocking it. Okay, so obviously what we had before is not that's not an irregular cycle. That's a very regular cycle. Okay, you just hit it one time and it does that forever. Okay, but in fact, every year, every day, the German economy, the American economy gets hit by shocks, and that's what makes it irregular. But the complex conjugate gives us more interesting dynamics, possibly, and it tells us how long it takes for the shock to be worked through. Okay, so obviously, if you have complex conjugate roots, you're gonna have an interesting dynamic, even working through one shock. Okay, so again, if you thought the collapse of the housing market in the United States can be characterized in an economy with this kind of behavior, you'd expect to have an echo, but an echo in another boom. You know, another housing boom will pick up, and then we'll have another crash, and even if we just have one shock. Okay, so let's go back to our original model now, and I'm going to show you very quickly how this can be done in matrix algebra. Okay, and this will close the circle. So, and you're going to have to really maybe spend some time thinking about this, and we'll come back to it next year. Next year, we'll do all this in more detail. Any model can be massaged and put in that form, but it's not so easy, and sometimes it doesn't work. Then we have to use matrix algebra. So take the same model we had before, the toy model. Remember, I wrote it like this, and I shocked it, and I showed there would be cycles. They're irregular. That's Slutsky. Okay, but now I'm gonna play the game of actually using matrix algebra to get that result. Okay, so it's easy. Okay, we're going to write the ASID model as a vector-valued difference equation. Okay, so instead of just yt as a function of lags, we're going to make y and pi together as a function of lagged values of that vector. And that's what macroeconomists do. If you understood what we did before and you thought it was easy, now you're going to be challenged a little bit. Okay, so I take what we had before, and I'm going to write it in matrix form. Okay, so this summarizes the entire model. Left-hand side, the endogenous variables in period t, and those entries in that matrix capture the cross-dependency in the current period. And then I've got the dependency on that. So this is an AR1 in a vector. Okay, this is a vector-valued AR1. That's a little bit easier to handle than a univariate AR5 or something. This is really convenient. So a lot of what we do is often trying to push our model into this form so we can play with it. Okay? So look at that. We've got the shocks, we've got the dependence. It turns out that's exactly the same thing as we had before, except now we have both inflation and output. So we're making progress. Okay? It turns out you can actually coax your computer to solve this thing. Okay, or to simulate it, and now you get inflation on the screen as well as output, and you can see how the shocks matter. Suppose I could turn off the demand shock, and I only had the supply shock. Suppose I could do that. Then actually inflation and output would move in opposite directions, just like the picture predicted last week. Okay, if demand shocks predominate, then you're going to have positive correlation. So there's no reason to think that inflation and output have to be negatively or positively correlated. You need to know about the shock. You need to know about the economy. You need to know the history. Okay, and or have a model that's rich enough where you can identify these shocks in a serious way. So a lot of what we do later is thinking about models that do that. So now, what do? I can invert the matrix to get it all on the right-hand side. Okay, looks pretty hairy, but it's not. Inverting a 2x2 matrix is something we can all do. And you get this vector-valued difference equation. It's a stochastic difference equation. It's vector-valued because now we have information on y, deviation of output from trend, and inflation, both. Okay? And that is really interesting because I can use the same logic I did before with the scalar model. I can now use vector and matrix algebra. Okay? So if you like, that's what A looks like. It looked so pretty before, right? It looks beautiful, but it's actually a very complicated function, just like before. It captures all the information of the model. You can think of it as encoding all the information, the dynamic properties of the model. And you can see that if I change one of these parameters like A2 or B1, I actually change the value of matrix A. I change its elements. Okay? So that's going to determine the dynamic properties of this version, the vector-valued version. And the cool thing is that this vector-valued version has the same properties that we had before. We can manipulate it using the lag operator. We can ask about the eigenvalues of that matrix. And those eigenvalues are actually the same thing that we had before. It's the dynamic properties of the system, but now I've got inflation in there as well. Okay, so I'm going to show you that, and then I'll say sayonara. Okay, so again, use the lag operator, but now it's a matrix polynomial. 1 minus a times L is a matrix involving powers of L. Only one power of L. L to the first power is equal to L. Okay? All I've done is rewrite what we had before. But if you believe what I said before, you should be able to invert that matrix on the left-hand side. And under certain conditions you can. I.e., if the thing is stable, I can do that. And I can use inversion. But before I do that, just think of what this is summarizing. This is exactly Slutsky, but it's even more compact than before. Okay? We've got the lag operator, the impact effects. Those are the shocks today. And A0 is kind of like the immediate translation of those shocks. So if I have a shock to supply, how does it affect output, and how does it affect inflation today? Okay, but we know that the model is dynamic, so that this effect will have to continue into the next period, and the next period, and the next period. That would be given by the propagation mechanism, and that's summarized by A. A is the model that expresses the lag effects of shocks on the current values of inflation and output. We talk about propagation model mechanisms all the time in macroeconomics. Now, so it could be many different things. One simple propagation mechanism that you can understand is depreciation. Okay? So if I invest in capital today, some of that capital will still be around tomorrow, right? The depreciation rate is 5% per year. Then after 1 year, I still have 95% of my capital around. And then in the 2 years, I have 95.95 squared. And it's declining geometrically. Okay, that's a trivial propagation mechanism. We think that things are more, like how do people react? Do they save or do they spend? That's kind of a propagation mechanism. Do they have habits? Is labor supply unpleasant? Is it so unpleasant that we want to smooth it out? These are different ways that people can smooth out shocks in the system. Okay? So if we invert this guy, this is what we get. So you can invert it. You can do that. You can invert this left-hand side and basically get exactly the same logic that we had before. We have a matrix hitting shocks, a vector of shocks. So it's just a compact way of writing what we spent a whole lot of time trying to solve for. Okay, so this is what a lot of programs can do for you. So you put a model into what's called Dynar. It's already cooked for you. I don't think that's a good idea. You should really learn first how this works and then use the computer to help you. Otherwise, it's going to be like the Matrix. Remember the Matrix? That scene, the guy's showing he's in that place, whatever it's called, and he's pointing to this energy source, and he says, I have no idea how this works. They're obviously all dependent on this thing, this machine, to generate energy in this subterranean world they were living in. If you haven't seen the movie, you should watch it. It's a great movie. Okay, so if we do that, we get we can use the properties of the lag operator. We can write it out, and just bear with me. You can write it out like this. That's the determinant of the matrix, and you've got basically this vector-valued function of shocks. And if you think hard about this, the underlying part, and I'm going to show you that formally, if you just write that out, you can actually get exactly what we had before. Okay, so let's multiply this out. Let's look carefully at the left-hand side. You can write those expressions as the trace of A, that's the sum of the diagonal elements, and the determinant of A, which is the determinant. Okay, and if you multiply that out, you get exactly what we had before. Okay, you can write. I'm going to go quickly because we're running out of time. You get basically the following AR representations of Y and pi. Okay, so you can see that you've got the shocks, you've got the lag values, and you've got the dynamics, which is determined by the properties of the A matrix. Okay, now of course in this model, E is not white noise anymore because it's a mixture of demand and supply, difference of demand. So the model structure is key to understand to get to this stage. You're not going to be asked to just regurgitate some. The model is the input that gives us more insights on where these determinants of the dynamics come from. The trace and the determinant, which turn out to be exactly the same thing as we had before. You study those things. They're linked to the eigenvalues of A. Okay, so if you're willing to put this in matrix vector-valued form, the eigenvalues of the matrix A determine its dynamic properties. And it's the same requirement as before. They have to be inside the unit circle to guarantee stability of the system. So if you give it a shock, either coming from one or the other types of shock sources, the dynamics we're expecting is that we have convergence, and that would be a restriction on the eigenvalues of A. Okay, so it turns out the eigenvalues of that A are exactly the values that we had before. So the lambda 1 plus lambda 2 equals the trace of that matrix, and the determinant is equal to the product of those roots. Okay, so if you went to do research in this area, you want to actually think about your model in terms of finding out what that A matrix is and what the eigenvalues of that matrix are. And you're basically solving this equation, which is exactly the same thing as we had before. So if you write it out, you'll get exactly what we had before. Now, I'm not going to ask you to do this, but you should know that there's a correspondence. You could do it the AR univariate form, and to the extent that you can write the model's solution as a univariate of order 2, you have the same answer. So you have stability defined by the eigenvalues, whether they're inside the unit circle or not. Okay? So there's the algebra. It's the same condition as before. So we have various cases, real valued roots, or you have complex conjugate roots, and then you have the same condition for stability. These roots lie inside the unit circle. Okay, so in general, I'm just alerting you to macroeconomics. We'll be spending most of our time thinking about simple models, but when you start doing more complicated models, you have lots of shocks. You have lots of variables you're interested in, inflation, output, possibly unemployment. It's the same thing. So there's a bunch of stuff you might want to be concerned with later. Conditions on the matrix A, which is very similar to looking at this univariate equation we tried to motivate with. Okay, so I started a little bit late, so I'll keep you for one more minute to remind you this is what it's about, right? It's about shocks. It's a propagation mechanism, that's the model, and the output is the stuff we can observe. Okay, so whether we do it in vector valued form or whether we do it in univariate form, to the extent that it allows that expression, sometimes it's not possible. So let me send you on your way with the following vision. After I've terrorized you with the complex conjugate numbers, I hope you have a happy holidays, and please come back in January. Okay, bye.